Thank you, Ian.
Something fun, so please go ahead.
All right, maybe to start with, this looks like a peculiar title in a way to speak on. What's happened is it's been 60 years this March since BCS came out with their paper, and I guess about 106 years since Reynolds discovered that mercury would go superconducting. So because of the 60 years, they're having a session, and I got asked to talk on this topic, which you might wonder about. The first is the question, why did it take, 46 years between Cameron and Onus and BCS? Well, you think about it, they didn't have quantum mechanics, and they had 2 world wars, and I don't think you can put a timing on genius. Things happen. And when Cooper understands the instability of the Fermi sea, and Schrieffer guesses a possible wave function, and Bardeen has long understood a great deal about the whole situation, the 3 of them write a paper, and I don't think you can talk about the timing of that. But I think what you might talk about is what was the atmosphere or the environment at that time, because that's perhaps interesting. Then you compare it, you say, well, Bednorz and Mueller discovered the ITC cuprates in 1986. And so you say, well, that's been 3 decades or so. When are we going to have a solution to that problem? And maybe one ought to add a solution that is agreeable to the majority of people, something like that. Well, that's again something I think hard to say, but I think one can again talk, what's the environment like? What's the environment right now like, so that is one optimistic, and I am optimistic. At any rate, let's start off, and we start off with old things you know. This is Cameron Onus, and he and his colleagues had cooled mercury down. They found it goes superconducting. And now, 46 years passes, and this is Bardeen, Cooper, and Schrieffer, and the famous paper that came out, along with an earlier paper by the 3 of them, and a paper just before that by Cooper. But now let's go back and see what was happening. So, and again, there's a very nice article by Jorg, I can remember his name, I reference him in a minute, in 50 Years of Superconductivity, Jorg Schmelian. A very nice article on this, but it seems to me that that we're going to see people, very famous people we know later on, making comments and ideas that seem strange. I always thought Einstein's was one of the most clever ideas of all. What he says is, look, we're going to need quantum mechanics, recognizing this was a quantum phenomena. So World War I comes.
He didn't use quantum mechanics in the paper he wrote.
I'm not. I didn't know Einstein wrote a paper. I know he had a theory, and I know the theory was there were long chains of molecules, and along this long chain of molecules, you could propagate electrons somehow without loss. That was an early idea.
It's a fascinating paper, not so much because of the theory, which was roughly the way you described, and he actually proposed an experiment. So it's beautiful. The most interesting thing in that paper is his discussion of how hard it is to be a theorist.
Yes.
And how easily nature will shoot you down. And I'm sure she's going to shoot me down. And he proposed an experiment, and then a few months later, it was carried out, and he
was shot down.
He was shot down.
Yeah, no, I had read this description, which I did not put up here, which is exactly as David says, how difficult life is as a theorist, and how almost always you do something and it's wrong. At any rate, these people did something, as we know, that was right, and of course is partway on the road to it. And in the midst of that is 1928, and Felix Bloch has ideas of how conduction electrons propagate in crystals. Of course, they scatter also. Bloch is famous, as you may know, for 2 theorems. One theorem, which is his first theorem, says basically that a superconductor carrying a current must have a lower state, or it's not carrying a current. Okay? Turns out that theorem is wrong. We'll come to that, except I think I pulled the slide, but I'll mention it when I hit there. His second theorem was that no theory of superconductivity will work. Okay, now we're progressing and experiments are kicking in. And we have the Meissner effect, which is finally giving insight that what a superconductor is a perfect diamagnet. Shortly thereafter, it's 1934, and Heinz and Fritz London are formulating phenomenological theories of the penetration depth of a variety of phenomena, along with Gorder, who has a two-fluid model. And in 48, I think London makes this marvelous statement that somehow superconductivity is quantum mechanics on a macro scale. In some way, Einstein was saying that. At least he was saying you're going to need quantum mechanics. 1950, a lot of things are happening in the Soviet Union. But by and large, a lot of that is not making its way to the United States. And Ginzburg and Landau are formulating a famous Ginzburg-Landau phenomenological theory that provides a marvelous macroscopic description of what's going on, and that Abrikosov then used to predict type 2 superconductivity and work out beautiful theory, of which he was awarded the Nobel Prize, as was Ginzburg, along with Leggett. Yeah. At any rate, there is something interesting here. There's an E star that I've written in here. And in 1987, a year after High TC, there was a meeting in Trieste. And Ginzburg was there. And Ginzburg talked about a number of ideas he had for High TC. But he talked specifically about E star. And he said he had gone into Landau because he had tried to fit some data, penetration depth data, and some specific heat data. And he had found that E didn't work nearly as well as 2 or 3 times E, and in fact, maybe 2.3 worked best. Landau told him, well, we can't do that because it doesn't satisfy gauge invariance. And as Ginzburg said at the meeting, how could we both have missed the fact that it could be an integer? Then Ginzburg went on to say something I hadn't realized. Ginzburg said that somehow, it must have been around 1950 or maybe a little before or after this, he had done a calculation of a charged Bose gas and found the Meissner effect. So I mention this to give you, as we'll go on, a feeling of what's the environment like. This is now 1950. Well, the environment, you might say, is warming up, at least, to some ideas that are to come. 1950, Froelich and Bardeen separately have decided that the phonon lattice would give rise to an attractive interaction between 2 electrons. Both of them then write a theory, but that theory is basically sliding charge density waves. About a year after High TC, I got a call from, California Electric Institute, I think. They were funding some of our research thinking about High TC, I think, that I was to come up to the Bay Area because there was to be a meeting. Well, what the meeting was for Edward Teller to explain his theory of High TC. And he had a T-shirt on that said, High TC. And his theory I found really quite remarkable in the sense that I don't think he had read much background on this. His theory was sliding charge density waves, basically. All right, now, 1950, some other things are happening. 1950, you have after the war, you have some people, and before the war there were people who knew about, who had been doing some of these, but after the war, they had access to a number of these isotopes, and so they do this marvelous experiment, and fortunately they do it on Mercury. On account of if they had done it on some of the other systems, it might not have been quite as formative as it was. But having seen now that the TC would drop to 0 if the mass of the lattice went to 0, it was a key indicator that the lattice was involved. Okay, And Bardeen and Froelich were also saying that.
What was the actual error bar?
Let's see, do I know? Answer is I don't know. Something I grabbed. Pretty nice straight line, though. All right. Now, we know in 1956, the remarkable thing that Cooper has discovered basically that there is an instability in the Fermi sea. And then there is an intermediate paper, and finally the BCS paper that lays out all manner of things, specific heat, transport properties, coherence factors. An amazing, of course, paper that shaped a century of physics. All right, now, I'm going back here to some of the things Jorg has written, which, if you get a chance, you would enjoy, I think, his chapter in BCS 50 Years. These are, failed theories. He's not making fun of these people, though, okay? Any more than I would like you to make fun of a set of things I'm going to show you about high TC, okay? And he says, look, here's Einstein's early idea that we mentioned. Kronig had, I think, a wonderful idea that somehow the kinetic energy was small enough that the Coulomb forces could freeze the electrons into kind of a chunk that would all move. How that was to work, I don't know. Bloch and Landau each worked with ideas of ferromagnetism. I think you can imagine, if you believe you have a ferromagnet, that means you have circulating currents. Now, those are atomic. On the other hand, they are circulating. Why not a bigger object to circulate? And so they thought those might be common cause. Okay. Heisenberg was going to use the exchange interaction. He was just a little too early. He should have waited till 86 or 87. At any rate, that didn't work out. London, I think, again, had this comment about Heisenberg's recent attempt, that it wasn't a condensation in space, but it was a condensation in momentum. But then he went on, he too believed, according to the literature, that the exchange interaction was somehow responsible for this. All right, this is the one I found most interesting. Always at Stanford, where I was in graduate school from 55 to 61, Shafrock was a favorite of Bill Fairbank. And this is from a paper by Shafrock in 54. And according to the book 50 Years After BCS, Cooper says he thinks Shafrock came to Illinois at that time and spoke on this, but he's not certain what the timing was. When you read this, I think it's quite amazing Shafrock has a paper like this. The problem is, what Shafrock's talking about are pairs that are forming on a very short distance scale, so that it is like a Bose condensate. And it took, now I don't remember the numbers exactly, 30, 35 years before we cooled lithium down cold enough in the atomic gases to study the crossover from BCS to Bose-Einstein condensation. And it is a crossover. So I think Shafrock, who was killed in '59 in an airplane crash, had some interesting ideas. And it's part of what I wanted to say. There are ideas at this time by various people that Bose condensation, that pairing, Mr. Ogg, O-G-G, at Stanford, has a wonderful idea. He's working with solutions of ammonia. And somehow he's miswired his experimental setup, and he's finding superconductivity until some nasty people from Bell Labs arrive and I guess convince him otherwise. But he had an idea that what was going on in the ammonia was a pairing of electrons, and that these were bosons. In 1956, at a meeting I think up in Washington, but at any rate, Feynman is speaking. Feynman had worked very hard on a theory of superconductivity, basically doing perturbation theory on the electron gas. Now, we understand now perturbation theory, even if you did it very well, isn't working for this. And so I think he makes a wonderful statement in his review, his talk at this meeting. And he says the only reason we haven't figured this out is we don't have enough imagination. And
Well, I'm trying to think, as you say we don't have enough imagination. I think there was a conceptual barrier, not just, because as you say, people were imagining things that were very close to a charge condensate. It's just that, how could you possibly
how could you possibly have a condensation of objects where the guys condensing might have 10 to the 6th pairs inside them?
That isn't a conceptual problem. That's a smooth crossover from one.
Okay.
The conceptual problem. So there was another great physicist at this time who thought about it. I doubt if it ever published anything, but Eugene Wigner worked on it, and he never accepted BCS. I remember well at Princeton that fierce arguments between him and Phil Anderson.
It
was never resolved.
I too remember it. I had been working as a postdoc with Bob Schrieffer, and we'd been doing some work on tunneling, trying to understand the frequency dependence of the gap and so forth. And I got invited by Dick Blankenbeckler, who you may not know but was at UCSB the time I came here. He was at Princeton. I got invited there to give a talk, and so I went and started to give a kind of colloquium, I guess, on the tunneling work I had been doing with Wilkins and with Schrieffer. And I didn't get too far into it before a hand raised by someone. As soon as he said a few words, I realized who it must be. He says, I shouldn't interrupt to ask this. I know this is, and then he went on from there, and he was just going to sink me, which, well, he might have. I had fortunately been at a meeting, Eastern Physical Society on the Eastern Seaboard, and saw what he did to a young person who didn't recognize who they were dealing with. And he wanted to know all about pairs and why should pairs form and all sorts of things that lay much beyond the tunneling talk I was giving, but were very good questions. At any rate, let's go on, see what I was reminded of next. Okay, well, we passed from this. I guess I wanted, sorry, there was something on the tip of my tongue. I won't do this at the meeting because I won't have time. 1956, 57. At Stanford at that time, BCS, of course, had published their paper. Stanford decided to invite Eugene Wigner to give a series of lectures on superconductivity. I sat in on that series of lectures. I didn't know much about it, but the distinct impression I had was two things. First of all, the BCS theory was wrong because it violated gauge invariance. And secondly, it was wrong because out of n squared terms, they'd only kept n. Okay? That's the impression I left with, and I'm afraid didn't think much about it until quite a few years later, I got to the University of Pennsylvania, and there was Bob. And Dan was there or was to come in a year. At any rate, let's move on before I run out of all my time. So it's 1986. Bednorz and Mueller have published a paper in, I would say, a rather obscure place. And the paper has this data, and it shows, look, something is going superconducting, possibly at about 30 Kelvin, which is just remarkable. Okay? Well, that comes out, I think, in April, but I don't see it, and I go to Japan for a meeting on quantum Monte Carlo fermions or something. And Kubo is there, and at a dinner, he sits next to me, And I should say, they know what's going on. They've seen this paper, and there are experiments reproducing some of this, okay? So Ryogo says to me, well, Doug, do you ever think that we'll have superconductivity above 30 Kelvin? Okay. Okay. I sat there and told him I was pretty certain that wouldn't happen. At any rate, I went to Kyoto, and a guy who worked with Elihu Abrams, who I knew, whose name will come to me maybe, mentioned to me this work and said, had you seen it? I'm afraid I told him no, but it's like some of the Russian work. There's all sorts of papers on higher TC. And what I should have remembered was Mueller had already been here? No, he'd been to, put it this way, I had met him already. I should have recognized we were dealing with someone serious. At any rate, not too much attention was paid until a December meeting of that year where, I should remember his name, where a Japanese physicist who had redone some of this spoke, and it was just striking. Kanamori, I think. It's not right either. Spoke on it. Okay. Let me give you a time period now. This measurement's made. It's 86 degrees, and pretty soon Paul Chu is measuring at 90 Kelvin. And Paul Chu makes his first talk here. We get him to come here. Paul Grant flies down because they're about to get in a custody battle over this, what's the composition of the YBCO is with Bell, which was settled in Bell's favor. But he comes down. And Schrieffer is here, I think. Yes, he is, of course. And so there's a neat day when Paul Chu, for the first time, publicly shows his data, which I should have put up here for this talk. 90 degrees superconductivity, just amazing. At any rate, people are saying at that time, is this superconductivity or is this something else? And you'd say, well, of course it has to be superconductivity. But I would say until these measurements, it wasn't completely clear. The first one is a flux measurement. They're measuring what the unit of flux in that thing is, and you can see it fits better hc over 2e. The next one is an AC Josephson effect, which is tricky. On account of they've taken a lead and they poked it down into the high TC material. You got to wonder where their contact is. Their contact is inside the high TC material, and they're pulling out a Josephson effect with a charge 2e. So I think at that stage people say, yeah, this is BCS superconductivity, but what's more? What's causing it? And what sort of state is it coming at us out of? Shortly thereafter, this is 89, Takagawa is measuring night shift, and one can see from the way the night shift goes to zero in this that you're dealing with a singlet pair. Now, some time passes, and you would have to have been around to see how the arguments went as to whether this was S-wave or not. The dominant group driving S-wave believed it had to be S-wave because if you had impurity scattering and had strong scattering between electron between one place on quote the Fermi surface to another where the gap change sign, then you would have an extremely rapid drop of TC with impurities, and that wasn't happening. Now, it wasn't happening on account of this superconducting pairing was really strong, okay? But it's one of the driving things along with whatever theory you had. If your theory was giving S-wave, my God, you were not happy with D-wave. Okay? Well, that was the case. And now Ziek Shen is making ARPA measurements. This happens to be a rather later ARPA measurement. You can see it's 2001. They weren't that good to start with, but they did tend to show, say, a 20%, a drop to about 20% there, as if there were a node. So that was support. I would say what really made it clear at the time, at least for me, were Walter Hardy and the group in Canada began taking time to make, and they had, Leon helps me, who do they have with them? They have this great crystal grower and chemist.
Doug Bond.
No, Doug Bond is microwave. There's the Ruchon. They have a man who focuses on making really good materials. And once they got the impurity scattering out, this went from T squared to T at low temperatures. And I think that made it very believable what one was dealing with. There were also NMR data that made us think this is what we had. But nevertheless, as you know, we're now into, 1993, 94, and there are phase-sensitive tunnel junction measurements. The first one by Van Harlingen's group has actually taken a crystal, put the leads on, lead leads on, as I've shown. They've then run a magnetic field parallel to the junction and looked at the maximum current you can get. And they see that rather than get the traditional dashed line picture, they're shifted by a pi half. And Kirtley came with a measurement. I decided I didn't have time to show, and now I'm really sorry. I wish I could fish it back out. It was a trijunction measurement. And what was fascinating about this was because of the way it was set up, the Josephson junctions would be frustrated unless it carried a current. And Kirtley saw it carried a current and had half a flux unit in it. Now, that's a stable system carrying a current, violating, in my opinion, Bloch's first theorem. Now, you can say, well, I've read some of this. People say, well, Bloch didn't consider the inductive energy. This stuff doesn't have enough inductive energy. It only has the phase locking across the Josephson junction. How that feeds in to a system where Bloch takes a Hamiltonian that consists of kinetic energy, potential energy, and then he talks about a ground state, and then he shifts the ground state to have some finite momentum.
Is this a macroscopic current, though?
Pardon?
Is this a macroscopic current?
All electrons are moving in this one. It's a wave function that's simply been shifted so as to have momentum. And then he proves that this state is higher in energy. If you would, now I forget what you have to do. You have to, I don't know, turn the current opposite the direction from something. But it's a minimal, it looks like a clean theorem, but it's clearly got something wrong. Or out of it, there's something not said that makes Kirtley experiment create the state that permanently circulates. Okay, we'll go on. I don't know more about that. All right, you can see this is 93, so you say, geez, you're making great progress. Only 7 years have gone by, and you got your grips on this. It's some type of roughly D wave, singlet, pair. Why don't you have a theory? Okay. Well, you had lots of theories, although some of them were scrambling to change from S to D. No names.
Well, you should mention that you weren't one of those. You don't have to be so modest. I think.
What I want to show you is something that I missed and that would have been a great help at the time. There was a meeting in San Diego around 1991 where Rossi Monod showed this data. What this data is, we have to look, one scan is momentum, one scan is energy. But what it's showing you is below TC in this cuprate, he's seeing a spin resonance mode. Okay? And he shows it. He goes swimming, and he doesn't come back. At any rate, I missed his talk, and
That happened in San Diego?
yeah. So what you have here is in 1991, you got a neutron scattering experiment that I claim we understood at the time, but didn't think about the experiment, nor did we think to propose it, which is a phase-sensitive measurement of the gap. It does so through a coherence factor, not through the tunneling way. And in that sense, it's very useful because you can use it on a variety of materials that you might find it difficult to make samples of to do the extreme type of work that Van Harlingen and that Suey and Kirtley did. All right. Okay. Now, Leon, how long do I have?
Not much time by ABS standards. Maybe 6 minutes left.
All right, we'll try and finish.
Yeah.
No. All right.
But we're more generous.
Thank you. So, what would it mean to say we understand the high TC superconductors. You know, maybe we ought to have an agreement and some signatures before that. Varma and Jorge Hirsch and I had a bet of a bottle of wine, whether it was D wave or S wave. Varma, the gentleman he is, paid off. Jorge is a stubborn person and a very good friend, and he has not paid off. At any rate, what would you say? Would you agree to this? Maybe we'd like to say we understood it if we could understand what causes the pairing. A very important question is, what phase are you going superconducting out of? I mean, BCS, somehow you had a normal metal. And you went out of the normal metal with a Cooper instability into a superconducting phase. Here, what are you coming out of? And then I've added this last one, but I think it's reasonable. We ought, if we think we understand this, be able to discuss whether this is a class of materials or whether it's one unique one.
Well, there's more than one.
There's more than one, David said. How come? Why do you think so?
I've seen the data.
Seeing the data on what, the iron superconductors?
No, but there's more than one.
I'm sorry. There are a lot of cuprates, so I should be careful and change that perhaps to, are there other classes, I don't know what word to use, classes of materials besides the cuprates?
I think what you should say is there are other materials where the answer to 1 and 2 is not, the standard BCS material.
Well, I would think that, what we want if we say we understand the cuprates is that we want to understand the mechanism of pairing. We'd like to understand the state out of which it paired and what are like the cuprates. Now, I'm not saying there aren't an entire other class out there that are going via bipolarons or via something else. But what class goes by whatever mechanism this is? So, I don't know. I think if we could answer these, some of us would quit.
Thinking of materials maybe that they're not quasi-two-dimensional, not layered material.
Well, some of those might still fit in here, Dan.
That's asking a lot, isn't it? Because you don't know what materials are standard BCS superconductors.
Good question. David asked, how do you know something is standard BCS material? I tend to agree with you, other than first I would look at the isotope effect. We all know uranium has a negative isotope effect, okay? So that doesn't work. On the other hand, you can then imagine, at least, looking at tunneling data. And I would claim if you give me good tunneling data, I can tell a lot about what the mechanism is and whether I want to classify it as being phonon-like or not, or being phonon. Well, now, there are many ideas. I've listed only a few. You may have some of your favorites, but certainly we'll come to the RVB, which is 1987. We'll get to that in a minute. I think that has some extremely key features to what Anderson said. We'll talk about that. Spin fluctuations, pneumatic fluctuations, phonons. I happen to know Mueller for years and years believed that it had to be phonons. And I mean, he's the person who discovered it. Forward scattering phonons, we have people here who are expert in that, sorry. Loop currents, which we'll talk about. Ampere, that's primarily Chandra Varma. Amperian currents, Patrick Lee, I suppose. Bipolarons. All right. I want to talk, in the time I don't have, about 3 of these to give a flavor of what goes on. So, in 87, a year after the discovery, Anderson comes out with a paper in Science, and he has some important things, I believe, in it. First is, he believes on the basis of the structure and chemistry that the Hubbard model is a reasonable model to start with. And the Hubbard model, the way I've written it down here, has a near neighbor hopping. Anderson also thinks it's layered enough it could be 2D. It has hopping, it has an on-site U, it probably has some T prime next neighbor hopping and so forth, but it's a very simple model. Then Anderson says in this paper, pairing was due to spin interactions via the antiferromagnetic superexchange, the mechanism, and then he's telling you what it comes out of. It grows out of a what? Novel insulating quantum liquid. That's what he's saying. Now those ideas are going to get modified as time passes. We're going to go through perhaps a 10-year period where it's interlayer tunneling. We're going to go through a period with Rice and Lee where I think it makes a lot more sense. It's a Gutzweiler projected state. But nevertheless, this was an early idea which I think, as one looks back, was, I think, quite close to the mark as to what the model should be. Okay, sorry, here's what I gleaned. What I tried to put up to say something about the RVB is this liquid, spin liquid, which is made up of these singlets. I've only shown short-range singlets.
That's your APS time ended.
That's APS time. Well, maybe I should quit.
No.
KITP ones are different.
Absolutely.
So there could be longer RVB bonds. This is a short-range RVB, and the idea is the pairing interaction is J. Now there's an argument that's going to take place about 10 years after this. The argument's going to be about the pairing glue. And again, while I didn't show it here, Anderson has a lovely picture in Science of a refrigerator in which there is an elephant. Sorry, that's not true. There's a mastodon called U, there's an elephant called J, and there's a mouse called spin fluctuations. And his point is, with a large interaction like U, and with J around, who needs the mouse? I think physically his notion is J, as you know, is 4t squared over U. It's a hopping over and back. You pay a denominator U. Well, you might imagine if you wanted omega to come into that, you'd be putting an omega up against U in the denominator. And so this is a pretty instantaneous interaction. And that's his point about no glue. Okay? I'm sorry, I did have it. What I had in it. All right, so this is it. That's what I just tried to say. And now we're moving on to another idea. This idea had, oddly enough, been used in '86 for something else. There had been a workshop.
Coming back to your original point, why did Phil reject this way?
I think Phil predicted, what's going on at this time is, I believe Phil is driven towards the, I don't know if it's he says he predicted it, but I believe what he believes is the impurities would kill D wave, and therefore these singlets that he's forming must be S wave-like. Now, to be fair, what's happening at that time is Colloquium is taking some of these ideas about projecting, and these ideas are flowing now out towards Rice and Colloquium and company, and they're taking Gutzweiler states, which is a ordinary, roughly ordinary plane wave of some kind, and or a BCS state in their case, and then they project out any double occupancy, and within that, if you then use the TJ model, and you factor J SI dot Sj, that SI dot Sj can be factored into S plus and and D wave, extended S wave and D wave states, and the D wave is lower in energy, and they had found that out in '87. But Phil, pardon me, I don't know the answer to your question. But at any rate, Phil had moved on almost by then to interlayer pair tunneling, which was knocked down because Josephson coupling between the layers wasn't strong enough to support those ideas. Let me leave this and go on. In '86, there had been a workshop here that John Wilkins and I ran, and Jorge Hirsch and a graduate student of mine named Eugene Lowe and I had been trying to understand how heavy fermions might go superconducting. And although their band structure was way too complicated for us, we thought maybe spin fluctuations could play a role. And so we were looking at that problem and found that the dominant, in a spin fluctuation model, the dominant pairing symmetry tended to be D wave, and we were interested in that. So when the high TC came along, we were interested in it in terms of spin fluctuations, with an idea that somehow you have a chi of Q, which at low temperatures is peaking. You can see out at pi pi. It's a doped antiferromagnet. This, on the right, that is called V, is actually a numerical calculation of Thomas Mayer with a Hubbard model. But I think the thing I'd like you to see is there is a strong peak, and that's coming basically out of the fact you're dealing with short-range spin fluctuations. I think we never got across to Phil the picture that we were not dealing with some long-range, low-frequency, long wavelength object, but we were dealing with a very short-range, near-neighbor, next-near-neighbor spin fluctuation. Be that as it may, that's what this theory was based on. And imagine, although we didn't do it this way, but you could take a BCS equation sort of and take a potential like that. You're going to have strong scattering, if I could work the light here, you're going to have strong scattering between states at K and prime and minus K prime if they transfer through large momentum, because that's where the juice is. And that interaction is positive. It's not like the electron phonon. It's positive. And so if you change the sign of the gap, you can solve this equation, and that's sort of the D-wave picture. Let me move on for just a minute to the iron pnictides. Here's a Fermi surface, this is a poor man's Fermi surface of some whole Fermi surfaces and some electron Fermi surfaces in this iron superconducting material. And now I'm going to imagine I have a state K prime and minus K prime, and this time I'm going to scatter them through a momentum Q, and they're going to go to minus K and K plus Q. This minus K object is really somewhere over here, I suppose. At any rate, you might imagine that if I have a spin fluctuation interaction in this material, I can play the same game if I change the sign. And Igor Manson and David Singh and company proposed that the iron arsenic type superconductors were going by this type of mechanism. All right, now, got a picture. This is a 35-minute talk, so we got to be moving on. And moving on, we're going to go to pneumatic interactions, which Steve Kivelson, a number of other people have looked at, we've looked at. What do they do? Well, first of all, they're attractive, like the phonon interaction. They got a minus sign in front. They're small momentum. Somehow here is meant to be some stripes. Here's some sort of pneumatic structure. So this is a small momentum object. What can it do? Well, it's okay. If you have a big U that doesn't like things sitting on the same site and is repulsive, and you have a small momentum attractive interaction, it can scatter you in regions where the gap does not change sign. I think primarily one tends to think of this interaction as helping some other major interaction. Nevertheless, it's been proposed. Now we come to a third kind that Chandravarma has proposed, which involve various types of loop currents on a copper oxygen lattice. One of the differences here is before we always were thinking about a cuprate, which has a copper oxygen lattice, but we were simplifying it down to being a simple Hubbard model, Zhang Rice singlets, whatever you want to use. We were simplifying it. Here, Varma is saying you better use the full copper-oxygen model because what's going to be important are circulating loop currents that go between the coppers and the oxygens. When this came out, I certainly thought it was unusual. He wanted to use it for a very interesting purpose that I have not talked much about. I said, we want to know, if we think we understand this stuff, we'd like to know the cause of the pairing, but we'd also like to know something about the state out of which it's come. Well, I'll show you a phase diagram later on, but the state out of which a lot of this stuff comes, particularly under dope, it's called a pseudogap state. And the question is, what's the pseudogap due to? And Varma's solution for the pseudogap is that it's an actual phase. And it's a phase characterized by loop currents. And people doing neutron scattering, people doing now very time-dependent NMR experiments seem to be seeing something at the T star line. And that, something, seem to be seeing something that could be these loop currents. At any rate, Varma's theory is built on having the loop currents. They fluctuate. Now, what's interesting about it is they fluctuate such that in the normal state, that interaction that scatters the normal electrons, or put it this way, the normal part of the self-energy, is not very K-dependent, almost no K-dependent, and it has a frequency dependence like marginal Fermi liquid, meaning it's pretty flat out till you get to half an eV or more. Okay? Not much structure. Quite different than the spin fluctuation interaction. And, there I've drawn it. When it couples to the pairs, there's a curious K cross K prime from the way the circulating currents interact with each other. And it's out of the prefactor, the K cross K prime, that he's going to pull the D wave. While the interaction itself is basically momentum independent and really rather featureless out to high energy. Okay. T star, the nice part of this is he's going to tell you what state he's coming out of. He's coming out of, a pseudogap state that's characterized by a time reversal broken loop current phase out of which the superconductivity comes. Okay. Now, what is the phase out of which this thing comes? Since so far we don't know the mechanism, maybe we don't know the phase, but I've thrown up some possible mechanisms. We could talk about others. Let's look at what phase it comes out of. This is data by Louis Taillefer and his group, which I find very interesting. It's YBCO data. The top part of the data is magnetic field being 0. And these are various types of measurements that I will not go through that range from transport measurements to optical measurements of various kinds. And what is being shown is what he feels they find. That they find an and this is doping. They find an AL phase. They find evidence of an SDW-like phase, but it may be a spin glass. They find, they find a superconducting phase, but if they dope it with about 6% of zinc, that knocks the superconducting phase down until this looks like the superconducting phase. And if they apply...
The blue points are a phase boundary? Mapping out a phase boundary?
I should show points. There's no points on these things, but sorry, this has points. The rest, I think, are data he's had in some other ways, not showing you the points. As far as what these are, those are carried over from NMR measurements that are suggesting there are short-range SDW, perhaps stripe.
At those points.
At those points. Something's happened. Okay, what's happened down here? What's happened down here is he's put a 50 Tesla field on it. So he's crushed a lot of the superconducting stuff. He can't crush all. Well, with a strong a TC, as strong a pairing as this has, he can't crush this. But when he crushes it, what does he see? He sees evidence of a charge density wave phase, a spin density wave phase, and a superconducting phase. Okay. This is a recent phase diagram of Steve Kivelson and company. Now you can begin to see you're dealing, when I said you've got to have a theory that gives you the explanation of the pairing and understanding what state you're coming out of. Well, you can see that's not so easy here. There's antiferromagnetic, there's short range or possible SDW. If you quench the superconductivity, there seems to be a CDW striped or checkerboard structure that forms. There's superconductivity. There's evidence of pneumatic behavior. And so this is a very rich phase diagram. And you might at this point say, we'll find other problems. I want to tell you why you don't want to say that. Anderson told us one thing I believe. The Hubbard model is a good model for this. And I want to now tell you about recent numerical work. This is numerical work.
So,
Yeah.
so could you explain why you think that Hubbard model is an interesting model? And as you said originally that you said that Hubbard model is a good model because of the structure and the chemistry of the cuprates. So if I'm looking for other problems and they're not the cuprates, why is the Hubbard model a good model?
When you're looking at other materials, you say? That's another talk, David. I'd have to show you the layered structure of the other materials. But it's remarkable how close they are to each other. Even the multi-band iron. Yeah. The iron is described quite well by multi-orbital Hubbard. Okay? It's not as two-dimensional. Okay. Yeah, you can make the problem harder, I agree, but it's believed that if you look at the Fermi surface of iron, they look like cylinders, which means it's quite two-dimensional. At least most of them look like cylinders. But
essentially what you're saying is there are a lot of ideas, but the Hubbard model is
right. So David's asking me, why do I want to stick with the Hubbard model? I'm about to show you. These are calculations on TJ models. Let's see, white stuff is on Hubbard, six-leg ladders. Why I have a text in there, I don't know. But these are recent papers, okay? And these are state-of-the-art numerical calculations, I would say, on Hubbard models. And what's remarkable about them is they are going to find that on a, let's put it this way. U is, say, the bandwidth, and the bandwidth is 8T. So you got a U of 8T, and the U is the bandwidth. Those are big energies. I'm going to tell you about calculations that are operating down at 0.005 T. Okay? Some of them at 0.001 T. That's about the condensation energy per electron when it goes superconducting. Okay? These are extremely accurate calculations on model systems on the Hubbard model. Let's take a look at it. What do they find? This is probably Troyer and Rice and somebody who's doing, what do they call it? Doesn't matter if I remember. IPEPs. It's infinite pair IPEPs. So it has to do with what basis they're expanding in. And they're very good numerical calculations. Plus they do DMR. They do 3 different kinds of numerical calculations as part of a Simons-funded effort. These are good calculations. One of the states they find looks a bit like this. It's an antiferromagnet, but it has holes in it. It's doped at 1/8. Okay, they find something like this. They find something like this that has not only antiferromagnetism, but it has D-wave pairing correlations. They aren't all that strong, but they see it. And they find something like this. This is a striped state where I filled the stripes. That's a striped state where they're half
Repeat
filled.
all the parameters fixed you just said.
Let's see what's going on here. These are the holes I've doped in. I haven't put a spin here because it doesn't know which way to point. Okay? So these are caricatures of the states they're finding. Let's see what else. Then they find this state. Take a look at that sucker. That's got stripes. That's got D-wave pairing, and they're in phase. Look at that guy. They got stripes, and the D-wave is pi phase shifted. That's the state which, when I get this talk fixed, if I go on long enough at APS, I'll show some, not show data, but at least refer to Tranquata and the group that have seen what they believe is this type of state. They believe it because a layer of it seems to be able to slide and behave like a Kosterlitz-Thales system. And how could you ever have that when you have another layer below it, unless there was something jimmying the coupling between the layers? And what will jimmy it, since they're in opposite directions, is if you pi phase shift the pairing. Okay? A very intricate state. What's remarkable is, once again, these are within 0.01 T in energy. All those states, okay, for this simple Hubbard model. Okay, why do I like that? Well, I wish I'd said. I got to put a slide in. I like that because of, sorry, no. I like that because of this. You got a model. You got a simple model that's doing stuff. I think that's remarkable. I think that's the reason to believe the Hubbard model has a lot to do with this problem. All right, now let's go through that and get to where we need to be. All right, let's try and answer. I mean, we haven't answered anything, but let's try and discuss the last question. What about materials? Again, I won't torture you with showing you their structures, which is very important, showing you what else about them, if I could remember, showing you their phase diagrams, how near they are to antiferromagnetism. But I will show you one thing. First, I'll tell you, I believe that this unconventional superconductivity started back here with Frank Sedlich's measurement in '79 of a heavy fermion system. Shortly after that, you have Jerome measuring a Bechtel salt, an organic. Then, of course, you have the high TC cuprate coming along. You've got a remarkable material here, plutonium, at 18.5 Kelvin. And this structure is a lot like this structure. It's just got plutonium in it instead. Then, of course, you have the famous iron materials that started off at 4.2 Kelvin and went on. Okay? I believe that this is a class of materials that fits what we're talking about. And therefore, when I want a pairing interaction and I want to state that things are coming out of, I would want it to be able to encompass a rather larger group of materials than just the cuprates. And, sorry.
Maybe you're going to answer this in relation, please, but a connection between, so you said the Hubbard model has all these almost degenerate phases, and that's good for high TC?
Oh, David asks an interesting question. We got all these degenerate phases. Is that good for high TC? I think you could see, if we remember back to the phase diagram where I put on a magnetic field to quench the superconductivity, you could see the CDW came on pretty strong. I would say mostly they're competitive. But when they get intertwined, I'm less certain what to tell you. But mostly I believe they compete.
Well, what's the commonality of this whole set of materials?
Okay, well, that's what I'm coming to. The commonality, I wish I'd put in more pictures. The commonality is the crystal structure of the layered materials having magnetic ions in some square array. The commonality is the phase diagram, having superconductivity appear on the edge or near where antiferromagnetism goes away. And finally, the commonality is what I'm about to talk about, which is how might we tie these together for a simple talk like this. And the way I want to tie them together is through what Rosat-Mignot discovered, which is these materials are characterized by a superconducting gap that changes sign. This phase factor, BCS had in the original paper these darn phase factors, which always I found tricky to understand. They're beautiful phase coherent features of the superconducting state. This particular phase factor describes neutron scattering with a momentum transfer Q, and that E in the denominator is the square root of epsilon k squared plus delta k squared, and you can imagine if I'm on the Fermi surface, that's the magnitude of the gap. Okay, so this is delta k plus Q, delta k on top, magnitude on the bottom. Okay? So, in some circumstances, if the gap has the same sign, this coherence factor vanishes. And we're familiar with that with low frequency ultrasonic attenuation, where instead of seeing a sudden peak where there's a big density of states at the gap edge, you don't see it. It's the coherence factor kills it. Other measurements that you might make up at higher frequencies near the gap edge with ultrasonic attenuation, you see a real peak. That's because this thing comes in with the opposite sign. This is the sign for neutron scattering. So this goes for 1 if there's a sign change in the gap. And indeed, what happens is this is the kind of momentum transfer the neutron scattering is picking up. Rossi-Mignot picked up. Here, the background up above TC would be like this. Below TC, you see it. Now, it's also true that above TC, under some circumstances, you see a bit of a peak, but it really takes off below TC. Okay? So this is sign change. Let's take a look here at iron superconductor. Here you've got an iron superconductor. They're looking at a neutron scattering that would take you from the hole pocket to the electron pocket. And what you see is at 280 Kelvin, you don't see much. At 60 Kelvin, when they drop below TC, you see it. So it's sign changing. I've added one more here. This is a heavy fermion material. It has a very strong signature. And to my mind, that means it's part of this class of unconventional superconductors, which I have not explained the mechanism nor what it comes out of, but we've talked about things it can do. And what I don't have, because I haven't finished my talk, is some statement regarding my belief that the Hubbard model, which has many of these features, we can study the interaction in the Hubbard model numerically, and what we find is its spin fluctuations. Now, having said this, let me show you one more slide. I'm sorry, forget that. This goes back a long way. This is Jaeber, 1962, and he sees wiggles here, which he believes have to do with phonons, and so does Schrieffer. This is calculation later by Macmillan and Rowell. That's the IDV blown up. You see beautiful structure. Out of that, they were able to construct what the pairing interaction was. And this is a gold standard of something that's electron phonon and mu star. We could go into mu star. That's gold standard for it, okay? One would like to do this with high TC, but the problem is you have a gap which depends on K, it changes on the Fermi surface. So what Zhou and company in China have done with Varma is they've taken a slice through this Fermi surface and tried to study and understand what the single particle spectral weight should look like. And what they conclude, we'll hear about Monday. I've seen some of the results. Zhao will speak. Those results do not appear to support, I believe, RBV or spin fluctuation scenarios. They do provide support for the loop current theory. You can imagine Varma likes that. Varma's on the paper also.
Does the supercurrent phase exist in the Hubbard model?
The loop current, no.
You know that
If
you can't break the
we no numerical calculation has seen it, and Varma wants the loop current to appear in a 3-band Hubbard model of copper oxygen. As I showed you, the loops went through the oxygens and the copper. So he would say it's not there. Hubbard model has D-density. It has other current carrying things, but not Varma's state. What did I do? No, I've ended with that. Yeah. No need. Sorry. Yeah. Well, now you got to the part I haven't finished my talk. But it kind of ends with a whimper rather than a bang, I think.
Very small.
Very small. What's it say there? Direction. Oh, that's bad. Let's not get there. Sorry, I'll go back. My sense is the reason that this is a bit like it was in 1950, 54, is we've got a lot of we have some good experiments going out there. We have some good tests that are starting to look at both the K and omega dependence of the gap. We have at least one model, the Hubbard model, that seems capable within it of containing much of the physics we see. And therefore, I would say that while we're out 3 decades in 1 year, that by 4 decades, we'll answer these questions.